Hello and welcome to Contemporary Math Notes for 3.6. Today we're talking about Euler circles and syllogistic arguments. And today is a lot of fun. I really enjoy this lecture and I hope you do too. So our first example, it says tell whether the following statement is valid or a fallacy. So you'll notice this form is kind of the same as we were working with before. It says all horses are brown and all brown animals have fur, therefore all horses have fur. Okay, so does the conclusion follow from the premises? So remember, our premises are right up here, and our conclusion is right down here. So in other words, do these two things add up so that you can make this statement? So all horses are brown, all brown animals have fur, therefore all horses have fur. This is yes. The conclusion follows the premises. Now, can you write this symbolically? Well, when we look at this, all horses are brown, that could be a P statement. All brown animals have fur would be a Q statement. And then all horses have fur would be a third statement, R. In looking at this, if we were to make a truth table, we would say P and Q, therefore R. And if we looked at this, it would be very difficult to come up with a truth table, even though we know this makes sense. So no, we can't write this symbolically. In order to write it symbolically, we would need words like or, and, if, then. So we need to have our connectives here to be able to write this symbolically. Otherwise, it's not going to work. So this is an example of something we call a syllogistic argument. And syllogistic arguments use the quantifiers all, some, or none. So you can see here all horses are brown, all brown animals have fur, all horses have fur. So those quantifiers up here make this a syllogistic argument. Now, to solve this, we can't use truth tables. Okay, so that's not going to work to use our truth tables. Instead, we're going to use something called Euler circles. Instead. So Leonhard Euler was a huge guy in terms of logic, and he used these circles and coined their name. And they're kind of like Venn diagrams for logic. Now, when you look at a logical statement, the form of an argument determines its validity. So arguments can be valid even if the conclusion is false. So it's kind of a weird statement. We can make a valid argument even though our conclusion is completely false. And arguments can actually be invalid even if the conclusion is a true statement. So let's talk about how we can use these Euler circles. First, we want to tell whether the following statement is valid or a fallacy. And we have all horses are brown, all brown animals have fur, therefore all horses have fur. And just reading it, it kind of makes sense to us. But let's talk about how we can make Euler circles. So first off, it says all horses. So I'm just going to introduce this circle here that stands for all horses. Now, all horses are brown. So what that means is we have this circle which is everything that is brown, and notice that all horses fall within the brown circle. So that's how you write all horses are brown. Now next we have all brown animals have fur. So we have a circle here, and this green circle is everything that has fur. And so if all brown animals have fur, we're going to move our circles like this. So now you can see that anything that's brown also has fur because it's completely inside the circle. So this has been our setup of our premises. Now what we want to try to do is see, can we make the conclusion false here? So we have to say, therefore all horses have fur. Now if I try to move horses around, where can I move it? Can I move horses outside the brown circle? Well, the answer is no, because all horses are brown. So notice it's completely bounded here. Horses cannot go outside of that circle. So that's how our picture has to look. Now we ask ourselves, do all horses have fur based on the diagram? Well, you can see here in this green circle is fur, and all horses must be inside that green circle. So therefore, this is a valid argument. Alright, let's try another one. The next one says, all teachers are rich. Pete is a teacher, therefore Pete is rich. Okay, so we can see here we're going to have some circles. We're going to have a teacher's circle. So here's our teacher's circle. We got a guy named Pete. Well, here's Pete. Hi, Pete. And then we're going to have a circle that is rich. Okay, so now when we look at this, we say all teachers are rich. So here's our rich circle. And how would I show that all teachers are rich? Well, every teacher then must be rich. So they must go inside this circle. Now our next premise says Pete is a teacher. So where does Pete have to go? Well, Pete is a teacher, so he enters this circle, and Pete has to go there. Now we verify the conclusion that Pete is rich. So we just ask, is Pete inside the rich circle? Well, he is. So therefore, this is a valid argument. All right, let's keep on going. Here's a big thing, and you can see the font got bigger. It says always try to draw the Euler circles so that the conclusion doesn't necessarily follow from the set of premises. So this would make the argument invalid. Now if this can't be done, then the argument must be valid. Okay, so we try to draw it so that it doesn't work. If we can't do that, then it's got to be valid. Okay, let's take a look at another example. So we have all football players are strong. I want you to try to draw that on your own. Give it a try. So we need football player circle and a strong circle, and then all football players are strong. So here's football players, and here's strong. So hopefully you drew the football circle inside the strong circle, showing that all football players are strong. Now, we know Christine is strong. Let's introduce Christine. Whoa, there she is. She looks very strong and a little bit angry too. So all we need to do now is make Christine be strong. So that means she's got to be inside the orange circle. So Christine could be in here, or Christine could be in here. So notice she could be in the football circle, or she could not be in the football circle, and she would be strong in either case. So where do we put her? Well, going back, remember, we're trying to draw this so that the conclusion doesn't follow from the premise. So let's take a look at our conclusion. It says Christine is a football player. So can we make premise 1 be true and premise 2 be true while the conclusion is false? Let's see if we can make that happen. So if we put Christine in here, both premises are true, but the conclusion is true. If we move Christine here, both premises are true, but the conclusion is false because Christine is not in the football circle. Therefore, this is going to be the correct drawing to show that this is invalid, or we call it a fallacy. All right, let's try another one. Here we introduce a new concept called no. So no airplane pilots eat spinach. So if we have a circle of airplane pilots, this is all airplane pilots, and then we have a circle of everybody that likes spinach. When we say no airplane pilots like spinach, that means, whoa, we can't go inside that circle at all. So airplane pilots and spinach are going to be separated here. Now next it says Janet doesn't eat spinach. Oh, here's Janet. She's crying because she doesn't like spinach. Oh, so she doesn't eat spinach. All that tells me is she cannot go inside the green circle, but she could be anywhere out here. So again, let's try to make our premise be true, and make our conclusion be false. Okay? Let's see if we can do that. So we've already made our first one true because airplane and spinach are separate. Now we want to make sure that Janet doesn't eat spinach, which she's good here. Where would we put her so that she wouldn't be an airplane pilot? Well, if we put her in here, we see that both are true, but it would make the conclusion true. But because Janet could fall out here, okay, this means she would not be an airplane pilot. So this drawing right here would show that this was a fallacy. All right, let's move on. All kids are people. Hopefully you guys can draw that by now. So we have all kids, and then are people. So all kids are people. So we did make that true. Now we want to make some people are students be true. Okay. So here's our student circle. Now anytime you have the word some, these are the more difficult ones. When you have some, that means we have to intersect these two circles. So when we have some, notice that some people are not students, some people are students, and then some students are not people. So we have to make this intersection. Now this statement, however, doesn't say anything about the kids. So notice students can be here, or it could be here. And that would, both of those positions, here as well as here, make both premises true. But remember, what we're trying to do is make the conclusion false. So where can we put this so that all kids are people and some people are students, but some kids are not students? Well, if we do here, that means some kids are students. But if we go here, that means that that is not true. So this drawing right here shows us that this is a fallacy. The argument is a fallacy. All right, let's move on. In this example, no neurosurgeons eat licorice. Go ahead and draw those circles on your own. Okay, the next one, it says all college graduates eat licorice. So go ahead and make a college graduate circle so that all of them eat licorice. Okay, so that word all means it has to be inside the licorice circle. Now again, we want to try to make both of these true and make this false. Okay, so it says no neurosurgeons are college graduates. Right now, is that a true statement? Well, right now, the way we have it drawn, it is a true statement. Now, is there anywhere else that we can move college students to make that a false statement? Well, can the college students go outside of the licorice circle? Well, it says no, because all college graduates eat licorice. So we can't move college students anywhere else that would make this false. Therefore, since we can't do that, it means that this is going to be a valid argument. And this would be the drawing to show that. Alright, so just a summary of our Euler circles to help you when you're making these. So the first type is when we say all. So all P's are Q's, meaning that circle P has to be inside circle Q. Another one we can have are no P's are Q's. So that means we're going to have two disjoint circles, meaning they don't intersect at all. And then a third type we can have are some P's are Q's. And when you have some, that means they have to intersect in at least one spot there. Alright, so this has been Euler circles and syllogistic arguments. Thanks for watching, and we'll see you in class.